Hello, I am James Malone. I am a product manager at Google and also a member of the Apache Beam PPMC. And I will be presenting with the other Eric Schmidt, who is with Google Developer Relations. And today we're going to talk about the next generation of data processing and open source. Specifically, we'll be talking about the Incubating Apache Beam project. So really quick overview of what we'll be talking about. First, I'll be framing everything up and talking about the things, well, I call it the last generation. Unfortunately, it is most typically the current generation. We'll then talk about the future, how things should work, what you should be able to do. From there, we'll talk about Apache Beam as a way to do next generation data processing. We'll talk about why Beam matters. We'll have a demo where Eric is going to run through some actual real live use of Beam to substantiate what we're talking about so we can show in addition to tell. And then finally, we'll leave with a few things to remember and some next steps and how to get involved in all of that. So let's talk about the last generation. These are common problems that exist in large data processing. I say last generation again, but many of these problems still exist today. So setting up infrastructure. A lot of tools in the data processing ecosystem are a blessing and a curse. They're a blessing because they allow you to do things that you couldn't do before. They allow you to tackle big new problems. MapReduce is a great example of this. Unfortunately, the process to use these tools is often very complicated. You have to decide on tools, read a lot of documentation, get your infrastructure, set the tools up, tune them. Often you have to go find experts because you're more familiar with your data, not the tools, and it gets very frustrating very quickly. Second, programming models. Now, you may have batch and stream use cases, or you may classically do a lot of batch processing. You're interested in streaming. Well, with a lot of programming models, you have to use two separate models. There's not one unified model. So for batch use cases, you live on Earth. And for streaming use cases, you have to go live on Mars in terms of models, which means that either people are never going to really be able to specialize in one model, or you have to have separate groups for different use cases. It can be a real mess. And third, portability. So let's say that you want to create data pipelines that are going to run in multiple places or in multiple runtime engines. Well, you can. That's the good news. The bad news is you're going to have 3 different data pipelines because those pipelines are going to be specific to the execution engines where you run them. So this may be, and it's even within execution engines, different versions of those engines may have incompatibility. So the blue may be Hadoop 1, the yellow may be Hadoop 2, the red may be Spark. You have a whole host of data pipelines now. So infrastructure typically is a pain. Models are disconnected, and pipelines are not portable. There should be a better way, and we believe that's sort of what we classify as the next generation of data processing. Infrastructure should be an afterthought. Models, whether you're using batch or stream, should be unified. And your pipelines should be portable, both between environments where you execute them and the execution engines that you're using to execute and run those pipelines. So in this new world, you should be able to decide on a product, just skim the documentation, and get going. Most commonly, I look at this as akin to renting a car at the airport. You can rent a car at the airport and know that it works because every car is very familiar and they're easy to understand. You don't have to go figure out where the turn signal is in cars and figure out the 5 different pedals on the floor. It should be very simple as just getting to it and using it very quickly. Models should be unified. So if you have batch use cases, if you have streaming use cases, they should work together in a unified model on a runner, and you're good to go. You shouldn't have to worry about which pipeline you pick or which model you pick for your batch cases and which for your streaming. And for your streaming, do you pick A or B? You should be able to pick one thing and do many things with it. Your data pipelines should be portable. So you should have one model, one data pipeline, and the ability to run it on multiple execution engines. For example, you may want to create a data model where you process a bunch of data in a streaming environment and then go run it on Apache Spark in one cloud, or Google Cloud Dataflow in Google Cloud Platform, or Flink locally. We believe that's how things should work. So why does this matter? I typically refer to this as my famous Pac-Man graph. So you should really be hands-on with your data and not hands-on with your tools and infrastructure. Even if you're 50-50, which I think would be optimistic in many cases, you're still spending way too much time with your infrastructure. The bulk of your time should be for you to be very familiar with your data, and the tooling should be there to assist you, not present another challenge. Apache Beam is a solution that tries to address many of these pain points so we can move from a somewhat painful place of current and last generation data processing to next generation data processing. So what is Apache Beam? It's a few things. It's first a programming model that unifies batch and stream processing. And I'll talk about the legacy of this programming model in a bit, but the reason I want to talk about the legacy of the programming model in a bit is this isn't something that just came up. This is based on a lot of innovation and research that came out of Google, and it's something that is now part of the Apache Beam project. Second, it's a set of SDKs. There are currently approximately two. Python was recently brought in, or is in the process of being brought into the Beam project, but there's a Java and Python SDK. Those are two of the starting SDKs. In the future, you will probably see others. And it's a set of runners for executing Apache Beam pipelines on many different processing backends that are doing distributed data processing. So Flink, Spark, and Google Cloud Dataflow are the three runtime engines external, potentially, to your local environment. And there's a local in-process runner for executing pipelines locally, generally for testing. In the future, we're also focused on creating new runtime engines or new connectors so you can execute Beam pipelines on additional processing backends. So a few ideas, potentially, are things like Apache Gearpump, which is incubating, Apache Apex, maybe MapReduce, many others. Ultimately, there is a vision with Beam. And that vision is that we focus on three different use cases. One, there's end users who want to write pipelines in a language that is familiar. So typically, this is the use case that you would focus on for creating data pipelines and allowing people to create data pipelines and go execute them. Second, with the Beam project, we want to focus on SDK writers. And these are people who want to make Beam available in new languages. And this involves quite a bit of work, but if done right, will allow for new SDKs to be added to the project with as little pain as possible. And third, runner writers. So this is making it possible for people to create new runners to execute Beam pipelines on other parallel distributed data processing engines. So these are the other, either the current ways to do it or what will come next year. And if history is any indication, there will probably be several in the next few years, and some of them will probably be, the next big thing. So Beam is really joining several threads of development into one open source project. And the reason I want to talk about this is to really make it known that this Beam is not just, it is a new project, it is an incubating project, but a lot of the ideas and engineering effort that went into Beam have some very deep roots. So Google wrote the MapReduce paper way back when. From that, you had two ecosystems develop. You had an Apache ecosystem, and a tremendous number of awesome open source projects designed to tackle either large or somewhat more granular problems in a way which was open and just truly great. You also had Google that was locked into specific file formats, had specific tools, specific problems to solve, but a lot of innovations were developed within Google to try and solve those problems. And these are really big data problems. From that Google Cloud Platform, developed two products to take advantage of these two sort of trains of development in a cloud platform. And with Apache Beam, from the Google end, what we're attempting to do is bring a lot of the innovations that occurred within Google to the open source community and really rejoin some of these threads. So really leverage a lot of the existing work that has already occurred in the Apache community and deeply integrate into it and have a truly open source way to take advantage of a lot of the innovations that have come out of Google. We're really focused on building a community with Apache Beam. And with that, we really want to focus on collaborating with new community members and growing a community that is diverse and vibrant and engaged and brings a lot to the table. And at least from the Google side, we're also learning quite a bit about involving ourselves in a larger open source community under the Apache umbrella. So it's proving to be a truly tremendous learning environment and experience for us. So our roadmap, it is fairly short, which is why I prefaced saying Beam is a new project, but certainly based on some deep roots. We entered the Apache Incubator in February. In early 2016, which we're basically out of, we're now kind of in mid-2016, there was a lot of designing, the beginning of refactoring. Very recently, and my virtual hat is off to the entire Apache Beam community, we had our first incubating release earlier this month, which is great. So it was the very first release, which was really focused on validating processes, how we were going to develop, meeting a lot of the very specific ASF requirements in our first incubating build. So we're actually really happy to have gotten that first release out. And towards the end of the year, we're focused on multiple runners that can execute Beam pipelines, with the ultimate goal by the end of the year, you'll be able to run pipelines that are created in Beam on many different distributed processing backends. So why Beam matters? I'm going to give you a whirlwind orbital view of the Beam model. As a stub, there's a second Beam talk tomorrow, led by Davor, who's also a part of Apache Beam and on the PPMC. And he's going to go in much more depth. So if this is interesting to you, I just want to throw out that there's going to be a second talk that will go into much more of the specifics. So Beam provides a next generation model for data processing. Often you're shoving a lot of the ways that you want to process your data pipelines, well, a lot of ways that you actually want to express your data and process it into the typical MapReduce shuffle framework, which is not great in some cases and can be quite constricting. In Beam, you create pipelines, and these pipelines are a graph, and it allows you to do a lot of really cool things. A few examples, you can process infinite streams of data. You generally don't need to worry about the types of data that you're going to process. It allows you to tackle a lot of data processing problems, which are hard at best or impossible at worst in the previous generation of data processing. So let's look at a few examples. Let's take, and I apologize, I'm going to back up. As a few examples, let's look at processing time and event time. And this is actually a critical component if you want to do stream processing. So processing time is the time that an event is processed. Event time is the time that an event occurs. If you're doing stream processing, the two can become very important. Say, for instance, we have a mobile application that's firing off triggers and events, and my logging system is capturing it, and I want to go process that data. In an ideal world, you process events exactly when they originate. Unfortunately, we don't live in an ideal world. So in this example, one of the elements that is circled, number 3, is just being processed a little bit after it occurred. So maybe this was just like temporary network lag. In another case, we have an event that is processed way after it occurred. In this case, several minutes. So somebody may have been in an elevator. There may have been a much longer gap in like cellular coverage. When you're doing stream processing, this can really matter, and Beam can help you address problems like this. Doing so is dependent on asking a few questions. And in the examples I'm going to show you how Beam can help you answer these specific questions. So the first, what results are calculated? So in this question, we're really asking ourselves, what do we want to compute? And in this case, we're looking at scores from a mobile application, and we're just doing a simple sum. In this case, it becomes very easy with the Beam model to answer this question. This is a typical, like, classic batch processing use case. In this case, you can see that we're processing several events, and we're just creating a sum for every event that occurred over a period of time. This is a very basic example, but something that we can definitely do with Beam. Let's make it a little bit more complicated, and this is where Beam really starts to shine. Let's say that we want to create 2-minute windows and sum all of the scores within 2-minute windows. In many cases, this can be a tricky thing to do. With Beam, the model and the SDKs give you the power to break all of the computations up into windows. And in this case, you can see that as we go through the windows, we're creating simple batch sums for how many events occurred in each window, or whatever the scores were in each window. But that means that you have to wait till the very end of whatever your processing time is to actually get your final result. What if you wanted to start getting results before you were done processing all of your data? This is where it starts to get really complex. So in this case, we're going to use a heuristic that is a watermark to actually try and emit results at the best guess of when the results are done, or when a window has seen all of the results that we should expect it to process. So in this case, the watermark is the green line, and you can see that as we're going through the windows, the watermark is allowing us to actually emit a result for a window when we think that we have seen all of the events that are going to occur in that time period. So in the first window, right at just a little bit after the first event occurs, we get 5, and you can see it goes up. Unfortunately, this isn't 100% foolproof, right? There's an event here, it's event 9. We assume that we are done seeing events within that window, and it's left out. So the next question, this is where we get to much greater complexity, is how can we emit early results, but also still make sure that we're capturing the full breadth of results, we don't leave anything out. So let's use firing panes here and figure out if we can emit early results. And you can see in the Beam model, this is not complicated. This is not hard to do. We're not going through a ton of work to do this. So in this example, we're figuring out events that are on time and events that are late. And you can see that over the window, in this case, we're just doing a simple sum for the entire window. And I just want to throw out, you don't actually have to do that. There's many ways. You could throw out events that occur in total over the window. We could split this out and look at like early events and late events. But in this case, we're just going to look at the total number of events in the window, which is why in the first window, for example, you see 14, because we're doing the total sum. But we're able to look at events that are early, on time, and late. And this is really powerful because we can get early speculative results, but we also can get the so-called, like the final number, I guess is the best way to put it, without a tremendous amount of complexity in our code or the model. So ultimately, we went through very quickly an example which was just a classic batch example, a windowed batch example, a streaming example, and then a streaming and accumulation example. And as you remember, it didn't take a lot of code to go do all of this. Now, it's a simple example. We just picked like a random scores example to show summing scores, but it's really what we want to impart is that Beam is designed to help you solve these types of problems without a lot of added complexity. Something I also want to throw out is, and this is a common question from the Apache Beam community, is if I have a data pipeline, can I run it on every runner and sort of expect the same results? So this is taken from the Beam website. The goal is to support every runner and every runtime engine to the best extent possible, and then work within the larger Apache community to help improve the compatibility between Beam and other open source projects over time. But you can see that some runners have different varying degrees of fidelity. But the overall goal is to make sure that we have as much portability as possible, but also provide people a lot of really detailed information about what works, what doesn't work, to help people make good decisions. So with that, I'm going to turn it over to Eric to run a demo.
High five? All right. Good afternoon. All right. So as James told you, I'm going to show you a demo of an Apache Beam data processing pipeline running in 4 different runner environments. This demo is a stripped down version of some work that I had done a couple of months ago with Spotify on their next generation of ETL and data processing pipeline, and they were using Dataflow at the time to do this. And so I got to spend a lot of time understanding the event structure and how Spotify processes data. So this is a very, very stripped down version. The ultimate analysis of the previous work that I had done was that Justin Bieber was in fact the top played artist on Spotify. This was all fake data, so if you see Justin Bieber again. So let's get into some code. I'm going to show you, in essence, 4 different runner implementations. The first one I'm going to show you is the direct runner. So this will be run locally on my machine. Obviously, it's not going to take advantage of parallelization that you would get in the cloud or in a cluster, but it's a great environment for you to do your prototyping and to do your basic testing. Now, as James talked about, there are basically kind of 4 different things to think about whenever you're building a pipeline. I'm going to walk through them again. So to get started, you set up a set of options. So for here, I'm going to be using the direct pipeline runner. I set my options. You'll see this later on as I use Spark and Flink and Cloud Data Flow, the options change slightly. But what doesn't change is the rest of the pipeline structure. So the first thing that you typically do in a pipeline is that you will apply one-to-many transforms in order to read data in. And you're going to read data in as an item called a P collection. And a P collection can represent anything. So here I'm reading from my local file system using text.io, and I'm going to read some test data, event data, which is basically play information based on fake Spotify data. And keep in mind, you can use mix and match all different types of I/O. So I could say, read from HDFS and write to BigQuery, or read from GCS and write back into HDFS. So you can mix and match how you want to from an I/O perspective. Just so you can see my event data, that's it. And so typically, if you're off starting to write some type of processor, you're going to look at the format and then figure out how am I going to parse all this and parallelize it. We're going to use Apache Beam to do that. So I have my I/O written, and the next thing I do is provide one-to-many transforms on how I want to address this data. In essence, the what and the where in time. So the first thing I'm going to do is execute this transform called parse log transform. So I'll jump over here. And by the way I wrote this code, I intentionally separated all the logic out into various discrete transforms. It's a nice way that you can then go after the fact and recompose a pipeline using a transform. So maybe James had already written a transform to do this. I can bring that into my project versus writing one monolithic pipeline. So the first transform I have is called parse logs transform. It's going to take a P collection of string coming from I/O, and the first thing I do is I apply a pardo to it, or parallel do, and I will pass in this P collection of string, and it is going to return to me a list of string. So basically, I'm just going to go ahead and start parsing it out, and then I'm going to pass that list of string onto another pardo, where I turn that list of string into a P collection of event. Event is just a Java type that I created that represents all the fields in that log information. And one interesting thing to highlight, going back to James' discussion of processing time versus event time, with Apache Beam, I have the ability to tell the pipeline what type of time space that I'd like to use for this particular item. So here, I'm telling Beam that I want to output this item into the pipeline using a specific timestamp. So whenever it's processed against this timestamp, the timestamp that the event was actually created, or whatever time I choose it to be, versus the time that it was processed. So how many of you have ever dealt with backfill or batch processing, and you have to go back in time and figure out, okay, what time am I actually going to use from this event? So this makes it very easy to do. In streaming mode, I could use receive time as the time, or I could also alter time and use the timestamp. So you can kind of pick and choose what time space you want. So go back to the direct runner. So now that I've parsed and transformed, the next thing I want to do is filter and key. And ultimately, my goal here is I want to basically do a count of songs by minute, actually by hour, similar to what James was showing you with the score sample. So I'm going to flip over to filter and key. And kind of similar structure, except things get smaller. Here I'm taking a P collection of events, and I'm going to turn around and create a P collection of key value pair. So if you start thinking about what you maybe do in MapReduce terms, I'm starting to key everything so I can map them down. Here I'm basically just creating a key based on the track ID, and the value is the event. So then I pass it back. I'm also doing some filtering. So this is kind of nice, and mixing matching concepts. I'm also filtering out some information. So I'm taking everything out, removing all the impression event types. So I'm filtering down the amount of data that I want to process. And I'll go back. And then the next thing I do is window transform. Mine is very simple. Typically, I would spend maybe 10, 15 minutes writing some fancy triggers to demonstrate how you could do early emission from early arriving data, or how you address late arriving data. But if this is the first time you've seen it, this is probably the easiest example to look at. So I have my event data, it's keyed by a song ID, and I want to window this into fixed windows of duration of days. So any transform or combinator after this step in the pipeline is going to receive all the data, in essence, quantized or bucketed it into that day window. All right. The next thing is top play transform. So I want to figure out the top plays, and I will go, oops, there you go. So now I'm going to take my P collection of key data that's also windowed, and I'm going to apply a count to it per key. So I've already keyed everything, so go ahead and do a count. Basically, it'll do a shuffle underneath the covers, hand me back a number, and then I'm going to turn around and use another built-in function into Beam in order to take top. So there's a bunch of built-in functions, min, max, sum, et cetera. I'm going to use top in order to figure out what the top ones are. And then I'm going to turn around and send another P collection back into the pipeline, which will ultimately be written to disk using my output transform, which is very simple. I basically pass a P collection to text.io and tell it to write. Again, I can mix and match where I want to read and write from. Great. So I have my pipeline. Now I want to run it. I'm going to go ahead, and I'll set a breakpoint here, and I will go over to Direct Runner, and I'm going to run this in debug mode. So this is great because I now have the ability to kind of step through and look at my stack, look at my variables, do a lot of hands-on debugging before I were to say submit this into my Flink cluster or to Spark or to Dataflow. I'm going to keep running through and remove this breakpoint. This will run for a second. And if I go to my output file, oops. Come on, you can finish. There you go. All right, awesome. There's the results. So basically, these track IDs and these times were the top 10 out of the list. Right now, I'm processing around 10,000 events. So this isn't necessarily a big data problem. The goal here is to show you that this will work portable-wise. But as I say that, I'm going to go ahead and fire up a Cloud Dataflow runner and process around a few million events. So I'll go back to Cloud Dataflow, and I'm going to go ahead and run this in the background because I want to show you Flink and Spark as well. But this takes a couple minutes to get going. All right, so I'm going to kick off this job. In the background, we're compiling. We're going to submit our code out to Cloud Dataflow, and I'll show you what that looks like in a couple minutes. Basically time shifting here. So I showed you the local runner working. Let's go talk about Flink. So on my machine locally, I have Flink installed. I have another pipeline, which is the exact same pipeline, but this is now my Flink runner pipeline. The only thing that's different here is my pipeline options. So I'm going to go ahead and execute this, and I'll just run it straight away. Let's delete the output so we make sure we're not any sleight of hand. I'm going to go ahead and run my Flink runner, and boom. Now, the nice thing about the Flink runner is it's very verbose. It kind of shows you all the optimizations and the process, the progress that it's making as it's processing data. So it finished with the output. Let's go over there to my top information. Cool. And trust me, I've run the demo over and over again. The data is the same. So guaranteed results across the same data in the same graph. So great. I now have portability locally. But what if I wanted to run this in the cloud? I'm going to go jump into my Spark implementation that's running inside of a Hadoop cluster on Dataproc. And I've already uploaded my jar to my cluster, and I'm going to go ahead and rerun a previous job. So take this previous job, I'm going to clone it. I'm going to use my same cluster. It's a Spark job. There's my jar. I'm going to call the class called Spark Runner, and let's hit submit. So now, if the demo gods are working, and James is also working, we should see my Spark Apache Beam Spark batch job kick off. So there it goes. Spark pipeline runner starting to execute. Is now reading, but in this case, and I'll jump back in the code and show you that, I'm reading from Google Cloud Storage. I'm not reading locally anymore. I'm reading from Google Cloud Storage, and I'm writing back to storage. And it's evaluating the write, and my job is complete. So if I go back over to my output bucket, let me download this file, and I have to use Sublime here for a second. Cool. There's the output. Awesome. So local runner, Flink runner, Spark batch, and let's flip over to Dataflow and see how it is going. So I'm in the Google Cloud console, and there's my jobs that I've already submitted, and this guy is just starting up. So the difference here, this is why I started earlier, is that whenever I'm starting from scratch with Dataflow, I have no cluster deployed. I have no infrastructure running, so I have to go spin up my VMs. Great, so now this is off and running, so it's processed at around 50,000 events, 150,000 events. It'll keep chugging through. This will take around 3 to 3.5 minutes, and whenever it's done, it'll tear down all the resources. The exact same output, well, except in this case, because I'm processing a few million records, the numbers are slightly different. So let's go back. This is the code for my Dataflow runner, and we just talked about portability across 4 different runners. One other thing I want to leave you with is if I were to do this and resubmit this job, I've now just taken that batch job that I showed you and submitted it, and it'll now run in streaming mode. Now, there are some changes that you may have to make to your implementation, like you'd want to have an unbounded source. So instead of me reading flat files from Google Storage, I may read a stream from Kafka or a topic from Google Cloud PubSub. But functionally, the rest of your pipeline stays the same. Your windowing techniques stay the same. You can take advantage of triggering for later arriving and early arriving data. And you can use all the same combinators that you used either with the SDK or that you may have built yourself. So with that said, I think mission accomplished, right? All right. There you go.
Thank you. Excellent. So let's just recap what we just did. Eric awesomely created one Beam pipeline, and you saw that he separated out the logic of that pipeline, and when he went to different runners, really the biggest changes were just changing the options for the runners. There wasn't a refactoring, a rearticulation of the code to go run in all of these different environments. So we ran on Cloud Dataflow and Google Cloud Platform. We ran on Spark running on Cloud Dataproc. And then locally, we used the in-process runner and the Apache Flink locally as well. And this worked, and the results worked. And I'm going to hide the downloads window. There we go. And there were no problems. So this is why we say we're trying to really achieve next generation data processing here, where you can write once and generally run anywhere with very small numbers of changes to move large sections of code from here to there. So things to remember. Apache Beam is designed to provide portable pipelines with a unified programming model that allows you to solve very thorny, tricky, challenging data problems today. We would love for you to get involved with Apache Beam. So as I mentioned, we are in the process of building an Apache Beam community. The project itself is incubating, and we're really trying to grow interest and get a large set of people involved that are using Beam to play around and experiment and see how it works. And since it's an incubating project, as a disclaimer, keep in mind it's incubating, so don't download the latest incubating release and go build production pipelines today. If you do want to just try out the concepts of the Beam model in a somewhat more stable environment, you could use Google Cloud Dataflow because they're very similar at this point. But there's several ways that you can get involved with Beam. There's the Beam website. There's a couple great articles from some other Beam contributors. There's mailing lists. If you are interested, join the mailing lists. We also have a Slack channel. We have a Twitter handle. So really do get involved. I also want to thank Francis and Tyler. Many of these slides came from previous presentations that they put together and shared with the Beam community. So I just want to call out that we use some of their content because it's awesome, and they're very, very smart people. And most of all, thank you guys for being here. We really appreciate it. I think we have 4 minutes and 6 seconds if anyone has questions.
So who owns the onus of building the outputs? Like if I want to create my own output format for Druid or others, does the user has to write, or are we providing as a community right now?
So some of it will be already in Beam, but if you want something new, I mean, it's an Apache project, so anyone can contribute. If you have a great idea, definitely suggest it to the Beam community, because I think that's where a lot of ideas will get vetted, and the project will navigate according to where the community wants to take it.
I see. Thank you.
The other thing I was also going to say that in some cases, you may not even have to write a custom implementation. You could just use a transform to output or write data, say if you want to push data to Memcache or something like that. So it kind of comes down to, like, if you have a much more complex and you have lots and lots of data that you want to write, make sure that it gets parallelized correctly, make sure that retries happen correctly, then yeah, you'd write your own custom sync. So
I think there's a question right there.
As someone who's already using Apache Crunch to do fairly similar workflows, are you guys looking into doing something like what Crunch Lambda does done for, doing like L table L collection basically, and doing Java 8 lambdas, which are really cool?
That's a good question. I would actually defer. You should talk to Davor. He's right there. He could give you a much better answer than I could.
yeah. Yeah, and we do have Lambda support. My code intentionally was not written that way. I didn't catch the other front of the part of your question, but feel free to ask Davor. So he's that.
He's right there. We're going to just point to him. Any other questions? Cool. Thank you guys again.